Okay, today let us start the chapter with circles. Small tips of the circles, just a brief introduction. This is a circle. You can see that the circle is touching, the line is touching the circle at a single point. The single point. So, this line, when it touches the circle at a single point, this line is called as a tangent, and this dot is called as the point of contact. Point of contact. Okay. Now, in the second figure, we can see that this line is touching the circle at 2 points. This is the one point and this is the second point on the circumference. So this kind of line is called as a secant. So this is a secant. And here the circle is just a circle and the line is standing just away from the circle. So there is no intersection of this line. Next, we can see how many tangents can be drawn to a circle. You know that a circle is having many innumerable number of points, locus of points together join together to form a circle. So this circle is having many number of points, and every point you can draw a tangent. So that is why we can draw infinite number of tangent to a circle. Then the properties of tangent are, now if you have a circle, a tangent AB here, this is a circle, center O, AB is a tangent, and we can see that on the tangent there is a point D. This is the point D, and this is the point C, which is the point of contact of the tangent. Now, if we observe that, we can see that a straight line will have many number of points, collinear points, points lying on the same line. So, from every point to every point from a point outside the line, we can draw a line. We can draw a line like this. We can draw a line like this. Okay. So here we can see that this line OD is always greater than OC. Suppose if we draw another two lines to this from here, if we draw a line here, you can see yes, all are greater than OC because at the point C there is 90 degrees formed. There is a 90 degrees formed here. So when the 90 degrees is formed here, this line becomes the hypotenuse, and always the hypotenuse is greater than the other two sides. Hence, this side is always the shortest. Hence, we can say that OC is the shortest line compared to OD. OC is the shortest line to the tangent. Shortest line drawn from a point O to the tangent. That is the tangent AB. So we can say that this line from the center of the circle to the tangent is the perpendicular line. We learned in ninth standard that when we draw a line from a point outside the line, this line is always perpendicular to this line. We have proved this in ninth standard. Okay. Next, the tangent to any point of the circle is perpendicular to the radius at the point of contact. The meaning of this is the next question. The tangent at any point of the circle. This is your circle. This is the tangent. This is the point of contact. He says that the tangent at any point of the circle. Suppose this is the point on the tangent. There is another point on the tangent. That is a line, that point B is perpendicular to the radius of the point of contact, is perpendicular to the radius at the point of contact. Means this line, suppose you have got a circle, you've got a circle like this. This is a circle and you are having the radius. This is the radius. Then says that whenever you are touching the circle with the tangent, then the tangent touches the point of contact here, then we can say that this radius is always perpendicular to the tangent. This radius is perpendicular to the tangent, or even we can tell that the tangent drawn at this point of contact to the circle is perpendicular to the radius. Either we can tell this radius is perpendicular to the tangent, or we can tell the tangent is perpendicular to the radius. Both the meanings are the same. Next, here we start with the question. The length of the tangent from a point A. This is the point A. This is the length of tangent AB. It is This is the point A and this is the tangent at B. The length of tangent from a point A at a distance of 5 centimeters from the center. This tangent is 5 centimeters from the center. Figure is not given. You have to draw the figure. This is 5 centimeters from the center of the circle is 4 centimeters. Means this distance is 5 centimeters and this distance is 4 centimeters. We know that when AB is the tangent and OB is the radius, this angle is 90 degrees, because we know that whenever you're drawing a circle with the radius and the tangent, there are 90 degrees is formed. That is, OB is perpendicular to AB. Now we get the Pythagoras theorem, because this is 90 degrees and the side opposite to 90 degrees, that is OA, that is hypotenuse. So apply Pythagoras theorem. In triangle OBA, OA square is equal to OB square plus AB square. So what is OA square? We have been given as 5 square. OB square, we don't know. Find the radius of the circle. OB is the radius of the circle. We don't know OB square plus AB square. It is given as 4 square. 25 is equal to OB square plus 16. Shift the 16 this side. Minus 16 is equal to OB square. 25 minus 16 is 9 is equal to OB square, or OB square is equal to 9. OB is equal to plus or minus root 9. Therefore, OB is equal to plus 3 centimeters. So this is our 3 centimeters. Next, find a point P. From a point P, the length of the tangent to the circle. From a point P, length of tangent to the circle is 24 centimeters. Means from this point P, the tangent length, you know that the circle is touching at the point P. From P, the tangent is given, that is 24 centimeters. And the distance of P from the center, this OP, is given as 20, from the center of the circle. The distance from the and the distance of P from the center of the circle is 25 centimeters. This should be Q. The distance of the point Q from the center of the circle is 25 centimeters. There is a printing mistake here. This should be Q. So he's asking to find the radius of the circle. Same way, we know that this is the radius and this is the tangent. There is a 90 degrees formed here. So this became a right angle triangle. So this is the hypotenuse. Right angle opposite side is the hypotenuse. Therefore, apply the Pythagoras theorem. Therefore, in triangle OPQ, we get it as, just if you want, you can draw like this. This is your P, this is your center O, this is Q. OP we don't know. PQ is 24 and OQ is 25. Okay. Next, we get, apply Pythagoras theorem. We get here OQ square is equal to OP square plus PQ square. So now OQ square is how much? 25 square is equal to OP square we don't know, plus PQ square. PQ square is 24. Okay, so 25 square is 625. OP square plus 24 square. 24 square, if we don't know, just we can multiply, and we can multiply 6 4 is 16, 4 to z plus 1 9, 4 to z 8, 2 to z 4. We know that it is 576. So here we get 24 square is 576. OP square is equal to 625 minus 576. So the answer becomes 5 625 minus 576, that is 9 4 49. So 49 is equal to OP square. Therefore, OP square is equal to 49, or OP is equal to square root of 49. OP is equal to plus or minus 7. Therefore, OP is equal to plus 7 centimeters. Okay. Next question. Prove that the length of tangents drawn from an external point to a circle are equal. Means you have to prove that PA, this is the length of tangent, is equal to PB. So what is that we have to prove? PA is equal to PB. Now for this purpose you have to take the two triangles. We will take the two triangles, that is OPA and OAP and OBP. Okay. So we will start our proof. In triangle OAP and triangle OBP. See, we are having rectangle triangle. So where the right angle is there, that alphabet should come in the center. So consider this triangle. Let us shade it off. This this is our green triangle. Okay. So this is our green triangle. Next one, we'll consider this our yellow triangle. This is our yellow triangle. Now you see, here we have got two triangles. Just you can note here, we are comparing these two triangles. We can see that OA and OB are the radius of the circle. So therefore I can write it as, therefore OA is equal to OB. The reason is radii of the circle. Secondly, we get OP is the common side to the triangles. Therefore, OP is equal to OP, that is common side. Then we got it as, here we get 90 degrees, here also 90 degrees. Angle OAP is 90 degrees. Angle OBP is equal to 90 degrees. So here we got right angle, here we got hypotenuse, and this is side. How this is hypotenuse? How OP became hypotenuse? Because the side opposite to right angle becomes the hypotenuse. So we can tell that triangle OAP is congruent to triangle OBP by RHS congruency. You have to mention that by RHS congruency. So now what is that we have to prove? PA is equal to PB. After getting RHS congruency, the remaining sides will be, from this will be PA and this one will be PB. Okay, therefore PA is equal to PB. Reason is CPCT, that is corresponding parts of congruent triangles. Next, in the figure, show that the sides of the quadrilateral touch the circle. When they touch the circle given below, the sides of the quadrilateral touch the circle. Prove that AB plus CD is equal to BC plus DA. We have to prove this. So what we can do here, we know that this is a circle, and you see these are the points outside the circle. That is this point B, external point these are. This is also external point, this is also external points. And this becomes a tangent to the circle. So this is a tangent to at point of contact P. This is a tangent at point of contact Q, and this is a tangent at point of contact R, and this is a tangent at point of contact S. Now we know that from this point, this and this tangent and this tangent from an external point, they are equal. So what we can write, BR is equal to BQ. Then we can write next, AQ is equal to AP. AQ is equal to AP. Why I'm writing AQ this side? Because when I add BQ plus AQ, when I add these two, I will get the answer AB. Yes, now that is what we have to prove here. So that is why I have written this side. I have not written BR is equal to BQ and AQ is equal to AP. I have not written this because when I add, I will not get the addition in a sequence. Okay, next. AP is equal to, we got AP is equal to AQ. After that, I will write DP is equal to DS. Where is AP? There I will write DP is equal to DS. And where there is DS, I will write CS is equal to CR. CS is equal to CR. Now when you add, this is 1, 2, 3, and 4. Adding all the 4 equations, left hand side becomes BR plus AP plus DP plus CS is equal to BQ plus AQ. See, he's asking us to show that this is equal to this. Okay. Even we can take the other way around, so it will be easy for us to do. So what we will do, considering a LHS of the given equation. So what I will do here, there are two ways of doing this. We can do either of the ways. Therefore, given AB plus CD. But what is my AB? AQ plus QB. Now, so what I will get? AB is AQ plus QB plus CD is CS plus DS. CS plus DS. Now what is it I have to get? BC. If I want to get BC means I should get BR plus RC. So BR plus RC means where I can substitute RC in the place of CS. So I will substitute here RC. Where I can substitute DS, where I can substitute BR, where I can substitute BR. So I want to get BC. So if I want to get BC, I want BR plus RC. And if I want to get DA, I want AP plus PD. Yes, na? So substitute here what we will get in the place of AQ. In the place of AQ, can I write it as AP? Plus in the place of QB, can I write it as BR? Plus in the place of CS, can I write it as RC? In the place of DS, can I write it as DP? Okay. After substituting all this, we will get. Now, what do I get here? BR plus RC. Group them BR and RC. So, in the place of both of this, I can write it as what is BR plus RC? BC. So, this became BC plus. In the place of AP plus DP, in the place of AP plus DP, I can write it as AD. Hence, we have proved the RHS. We started from LHS and we have proved the RHS. Next.